Well, I've got some fluid samples. I've got one from a construction loader, and the test tape says it tested out as 23/22/13, if you know what that means. Got another one from a forklift from a construction company, from a forklift repair shop down the street from us. 23/22/15, if that means anything. Here we've got a sample out of a Caterpillar 308 excavator from our neighbor company, 21/17/9. And here we've got some brand new hydraulic fluid. And we've got some nearly brand new hydraulic fluid. Been running in a power unit here for about maybe a month or two. And yeah, our pop quiz question today will be, hey, if it looks like this, if it looks fairly clear, is that good enough? That'll be our pop quiz question, and we'll come back to that one a little later. Hello, this is Carl from lunchboxsessions.com. I'm glad you could join us again today for our fifth in a series of 8. And if you joined us in our previous live broadcasts and you saw Mark there with a little wrench next to his name, well, Mark Many Letters Pichalkowski is with me today in the live broadcast. He's isolated at home, but he's here to share his wealth of experience. Mark and I have been traveling the highways together for 15 years, providing hydraulics training at industrial sites of all kinds, providing hydraulics maintenance consulting, and we've had a lot of adventures together. But even before the time when I met Mark had been hard at work for a number of years, helping forest products related companies, plywood and veneer operations, get their particle contaminant issues under control so that very sensitive servo valves and proportional valves would perform at their very best. So Mark, very happy to have you and your experience with us here today. Thanks for joining us, Mark.
Well, it's a pleasure, Carl, to finally be part of one of these other than just typing on the side in the chat room. So it's a new thing for me, and I'm pretty happy about it. I even combed my hair today.
Hey, there you go. Well, yeah, when the camera is on, right? And all of us have multiple screens now. How many screens do you have there?
I have 4 going right now.
There we go. That's become the new norm for all of us if we're working in an isolated environment of some kind. Well, our humble thanks to all of you for the questions and comments and very encouraging remarks you've been sending us over the weeks we've been doing this. So we're just over the halfway through our spring and summer season of 8 live broadcasts, and we're just so happy to have you back if you're joining us again. And if you're new with us on this series, well, then a special welcome to you for finding our live broadcast, and great to have you with us. So let's have some fun today, learning a little bit about particle contamination. I guess it's only fun, particle contaminants, if we're studying them in theory. If you're struggling with controlling them and dealing with reliability issues in valves and pumps and what have you, then maybe it's not so much fun. But hopefully we'll be able to answer some questions for you here today. We'll look at typical hydraulic contaminant particles. What are they? What damage do they do? And I know Mark will have a lot to offer on issues of how you bring particle contamination problems under control. And you've probably heard about some classifying numbers. I was reading some numbers off to you a moment ago from these dark samples here, and maybe these samples have problems. Maybe you picked up on some numbers that you thought were, wow, that's dirty, or maybe you thought otherwise about some numbers. The ISO 4406 is a very common standard for referencing levels of contamination. It is so standard that it shows up on lab analysis reports. So we'll get into a little bit about how to use that standard. Even portable equipment like the laser particle counter that we've got here, we'll use that ISO 4406 also as a reference. So we'll need to learn a little bit about that, but we've got a limited amount of time, so we're only going to brush across the highlights of that. And then we've got the microscope set up, and we don't use that so much for precise particle counting. You can. There's another standard called 4407 from ISO that has a lot of procedures about how you use that type of setup. But we like to use it for relative understanding of what the particles are, what they're made of, what shape they are, what they look like, how many, and you're going to see some pretty neat pictures here in a moment. On a general note, every time about safety, do be very careful if you're sampling hydraulic fluid from a live running system. If you haven't done that before, then please don't consider our short time together today to be an adequate amount of training to do that safely. Hydraulic systems have pressure that can easily maim or kill, and there's temperatures that can burn as well. So if you're going to take some fluid samples live from a hydraulic system, work with someone who can mentor you and train you on that, someone who's done it before and knows how to do it safely. We're really interested in hearing where you're from, and some of you are already writing in to let us know that. And we're really interested in your questions as well pertaining to our topic today. And so you can use the YouTube live chat. If you haven't already done so, log into your Google YouTube account and you'll be able to type questions to us during the live broadcast, and we'll do our best to keep up. Really helps if you put that question mark on the end, then we can pick them out as quickly as possible. If you've got other questions for us that don't necessarily pertain to today's topic, then feel free to fire those to us as well. Email's great. info@lunchboxsessions.com is a great way. Or look for me on LinkedIn, Carl Dyke, Industrial Teacher. I'm pretty easy to find on LinkedIn. If you and I are not already linked, send me an invitation. We'll get LinkedIn together and we'll have discussions about other topics that you might have. And welcome so far to viewers today from Quebec, Canada, from the Philippines, from Mexico, from British Columbia, from Estonia. Wow, hey, visited there once. And welcome also from Peru, from Oklahoma in the USA, welcome, and from the United Kingdom, from Azerbaijan, from India. Fantastic. Great to have all of you with us here this morning. This is our 5th YouTube in the series of 8, and we're looking forward to seeing you back 3 more times. Our next one will be on June 23rd and will be about servo valves, some of the fussiest valves there are. So it's probably a good thing that we're talking about particle contamination today, so we get things set up right for that. A great shout out to my friends at fluidpowerworld.com. Fluid Power World is an excellent source on pneumatic and hydraulic components, on the latest thinking in hydraulic design, on system engineering, and keep an eye on the events tab on fluidpowerworld.com. In-person conferences are a little tricky to do this year due to the pandemic, but if all goes well, there may be an online virtual conference in the fall. Looking forward to meeting you at these highly educational, informative events where lots of good sharing and learning happens. Fluid Power World. Our sponsor today is SMC. With over 60 years of experience and offices in 80 countries, SMC is a world leader in automation and pneumatic technologies with highly specialized products for general manufacturing, for vacuum systems and chemical handling, for process and for life sciences. All right, welcome also to participants from Saudi Arabia and Turkey. Thanks for joining in today. So, as we usually do start out, we want to show you some photographs to bring as much reality as possible to the topic. It's going to seem a little bit microscopic, some aspects of our work, and so it's good to relate it to some hydraulic realities of what actually goes wrong, what do the problems look like. And so every photo that Mark and I are going to show you here is from our actual travels through industry, hydraulic components that have caused an issue and had to be taken apart, only to find out that contamination, as is so often the case, was the cause of a valve that jammed up. So what are we looking at here on screen? If you guessed directional control valve spool, you've got it absolutely right. And since I'm zoomed in here now, hopefully you can see the lateral scratches along the spool that let us know that some kind of hard particles were in there, and that's what was causing this valve to stick and not move when the solenoids were energized. From the same system, a spool out of a pressure compensated flow control. And again, if we zoom in on that and you look right here in the middle, you should see some pretty deep lateral scratches what was inside this system? That's our question. Well, here comes the answer. So with the armature, tube, and solenoid assembly removed from the end of the directional valve, if you're looking in at the push pin and the armature in there, you could see a circular spot with brown coloring. You've got it right. That's rust. There was a lot of water in this system. It was only being run on occasion, and due to the amount of water in the hydraulic fluid causing rust on the metal surfaces inside the valve. So these weren't even particles that got in from outside somehow, unless you're going to include water. Well, water is a particle contaminant, but generated other particles, which are those iron oxide particles. And boy, those are hard particles. They don't break down easily. You can even buy some grinding stones that use a type of iron oxide similar to what you get from rust, and so you can have an idea from that as to how hard those particles are or were. Mark and I are well accustomed to having a good look at a new valve manifold, making sure that where the threaded ports are from the machining, that there wasn't some little burrs hanging off. And sure enough, here's one that was shipped to us, and you could clearly see it in the photo that there is a burr about to break away from the first threaded machine, first thread there in the port. And watch out for those. Don't let those fall inside the system. Pump controller off of a Kawasaki pump, if I recall, and I can't remember what was all going wrong with that one, but what you can see is that an O-ring had broken down, and those O-ring bits aren't on the outside. They're somewhere inside the hydraulic system, having broken away in little pieces. We've seen that kind of damage before a number of times on different types of machines. Mark, you brought this one home, didn't you?
Yeah, we got that from up north on a machine that we had asked to have a look at the pump and try and figure out what caused the O-ring to erode and then, of course, send particles into the pump itself.
Right, and then here's another one Mark brought home from, I think, from a dump truck, sand spreader, and I believe this was the pilot section out of a relief valve on the end of a bank of valves, and you could see a bunch of stuff stuck in the screen. Do you remember what the issues were on that one?
Pretty much the same thing. Slow response going on. When we checked to see if seals were deteriorated, we found the screens plugged. That's just a sample of what we were trying to do.
Right, and a screen like this is not meant to be a filter to keep your hydraulic system and all your fluid clean. This is just trying to sandbag, if you will, against a major problem. And once that screen starts to plug up, you're still going to suffer difficulties with it. Oh my, this was a fun one for Mark, as I recall. We brought this valve unit home from a large container stacker loader, and there was problems with the boom drifting down. And here Mark had removed a damping orifice from behind a cartridge valve, and it had a sliver of polymer seal driven right through, probably from the glide ring on a piston and a cylinder, I'm not sure, but driven right through the center of that damping orifice. And here's the matching load holding cartridge, the check valve that was meant to keep that boom from drifting down. If you can see as clearly as I could see it, there's a little metal filing on the end of the valve. It's not trapped in the poppet right now, but it's so close by that perhaps it was. And if you look further back in that poppet, again, you could see some more of the seal that was probably coming from the piston and the cylinder and contaminating and keeping that poppet from closing. But you know what? So far, we're showing you particles that are quite visible to the eye, right? These are very obvious ones. Mark brought this one home too from an overhanging load that couldn't be easily controlled, and no microscope needed to understand what was happening here.
I can even see that with my eyes.
Yeah, so major chunks of material getting stuck on a poppet, and then you cannot expect the valve to perform. Where they come from has to be explored.
These are the pieces that we often refer to, that some of the major problems that happen with hydraulic valves. I've always taught over the years that keep it simple, that valves either stick open, they stick shut, or they partially stick. And these are the particles that cause a lot of our sticking and partially stuck valves, for sure.
Right, and then here's a collection of jewelry that Mark dumped out of a piston pump for a client whose pump came apart, and maybe contamination didn't cause the pump to fail. Maybe there were other issues. I think there were several pump failures in a row within a day or two. Correct, Mark?
Yeah, they went through 3 pumps in 6 hours
No, that's an
on a
unfortunate.
machine.
That's a bad day, but
Yeah, it was.
obviously, as this pump came apart, there were a lot of additional contaminants now spread throughout the system. And yeah, when a major failure like this occurs, how many machine operators, owners take the time to really strip down the system and flush everything out? And it is hard to do, very difficult to do. I think this is the compensator spool out of that same pump. And if you know a pressure compensator or a load sense compensator spool, you already know that the diameter is less than that of a pencil. It's a pretty small device and not too difficult to jam it up with some soft aluminum or bronze pieces getting in there, get that thing stuck so it won't respond anymore. Now you've got some major difficulties with a pump controller not doing what it's meant to do. There's the matching one for both compensators from that pump. Oh, I remember this one. Mark and I brought this one home from a very large telescopic cylinder where the counterbalance valve was built right in, and at the right time when the overrunning load was off the machine, this valve needed to be open once again to avoid pressure intensification on the rod side of the piston, and this valve was not opening up. And we took it home, and Mark, what did it take to get that valve spool to come out of the sleeve? You had to work pretty hard at it to get it out, didn't you?
Well, you started out with a little hammer and maybe a brass drift, and this one we ended up with a 16-ounce hammer and a steel drift by the time we got it out.
Right.
So it's never been made to put back together.
Yes, that's a good point. This was destructive analysis, but we wanted to find out what was happening. And as you could see there, here I'll zoom in on it. You could see the brushing marks, the scoring marks all the way around. This valve was seized tight due to silica sand that was jammed in there and just keeping that valve from responding or moving. These pieces are close tolerance, and if it's just clean hydraulic fluid, they slide back and forth so nicely. And other types of contaminants, hard particles like silica, are not meant to get in there. This one was wedged tight. And once we had it apart once and cleaned up, it was very easy again to slide those two pieces back together and see that they were somewhat back to normal. But to leave them stuck like this was quite a catastrophe for that particular valve. So you see that scuffing damage there. And that's just the items that we're showing you so far that are so easy to see with the naked eye. Now I'm going to switch over to a collection of images, largely from our microscope. And these are the very best from our years of playing with the microscope and sampling fluids that we know were a part of a hydraulic system that had some difficulties. And what you're looking at on this image, especially in the upper left quadrant, is a lot of little mineral stones that are in the neighborhood of 10 and 15 microns in diameter. How big is that, right? We're going to have to look at that in a moment and try to understand what a micron is, but just keep in mind that a lot of spool valves, if they're a servo valve, may only have 1 or 2 microns of clearance. A basic directional valve may only have clearances as large as perhaps 4 or 5 microns at the very most. Anything larger is leaky. So there's a lot of little mineral stones in there and a very long fiber as well. Again, a red fiber and some mineral stones. That red fiber, that's probably the color of the coveralls at that particular shop. Mark and I often find fibers of whatever the colors are for the shop rags or the coveralls that are being worn in that shop. Otherwise, lots of mineral pieces in there. Here we're starting to measure with the measurement software. We'll be doing a little bit of that, just a few minutes of that today. And you'll see that there is an object in there, a solid particle in there. I don't know if you can see it well on your screen or not. I'll zoom in. 79.46 microns long. Well, just to give you a bit more reference on that measurement, the diameter of a human hair is apparently somewhere in the neighborhood of 70 microns. So it's a fairly small particle. All right. Yeah, here we have an aluminum shaving. And yes, if we took that slide out and put it under the light and look carefully, if our eyesight is good with our glasses on, that 227 micron long aluminum sliver might be visible lengthwise, but depends on what its width was. And the width is not that great. Let's move along here at some others. Here's a good variety of minerals of different colors inside the system. Perhaps some of those black flakes may be carbon flakes from overheated hydraulics. Wow, that's a complete little rock collection right there from a very badly contaminated system. Probably some metal flakes and some oxide flakes, as well as lots of minerals mixed in there in lots of different sizes. In this one here, you even see a beautiful green gemstone there, and this is how we often see it when we start to look at minerals in a hydraulic oil sample with the oil coating still on them. They'll glow a wonderful color, but you're basically looking at chunks of different types of rocks. And then those very large tan color pieces that you see all over inside there, those are wood flakes. It's not uncommon in a forest products, a sawmill, or some type of a plywood production plant to find that there's lots of sawdust. It gets into the system somehow. We'll have to chat a little bit more about that. Is that one of our all-time worst? I think that's in our top 5 collection of very badly polluted hydraulic oil. Oh, this is probably a good time for me to tell you that what you're seeing there on that slide occupies not even a complete amount of one of the squares in that grid on that little filter element. 25 mil is only about a 1-inch diameter, and there's a good number of little squares there. And what you're seeing there doesn't even occupy one of those full squares. And the sample that hit that filter, that membrane filter we're going to play with in a moment, was only 25 milliliters, about 1 fluid ounce of hydraulic fluid. And that's all that was in that contamination, and then only a small fraction of it. So a very badly contaminated fluid. There, for the first time, you're seeing one of those membrane filter grid lines that you see on that. I don't know which camera will pick that one up the best, but you'll see those little bit of, that's about a 1-inch diameter, 25 millimeter filter, and that is divided up into those little squares, and so you're seeing one of those little black lines there crossing over the slide in the microscope, and lots of tiny mineral particles are only 2, 3, and 4 microns in diameter, and then some of the really big ones we measured there, 26, 135, 88. I better move along, but there's another good collection of contaminants, lots of minerals. Again, many, many minerals. And here's our last 3 or 4 images, which are probably the worst we've ever seen. And all of the ISO numbers for the 4406 on this image L and M here with the measurements. These were all up in the high 20s, mid-20s at least, for an ISO 4406 measurement. You've got metals, you've got sawdust flakes, you've got minerals of all kinds, little pieces of carbon in there as well. I like to include this one, photograph O, just so that you can sort of see the borderline between where the filter that we're going to work with here in a moment will draw a sample through the funnel into the flask using a vacuum pump, and that little filter I was just showing you a moment ago sits on top of a laboratory apparatus called a fritted glass base. And what fritted glass means is basically silica that's been heated up and almost fused, but it's still porous, and it makes a very smooth base to put the membrane filter on. And this membrane filter has pores that are only 1.2 microns in diameter, very, very small pores. And we're going to draw the fluid through and then try to trap the solids on top of that filter membrane and then move it to the microscope in the Petri dish. So you can see just the border edge on this image as we transition to the clean, empty filter under the glass edge. And this one was fun too. The gentleman who brought it to the course that we were conducting were laughing about it as they brought the sample in. They said this one will be really interesting. We're pretty sure no one ever serviced this metal strapping machine at the end of a packaging line in the 30 years that we've had it. It'll be very interesting. And I think that's the first time I ever saw contaminants that looked a little bit almost like rice vermicelli noodles, so badly contaminated, and just giving us some reference for what the reality of it really looks like. So, I took a sample today from hydraulic fluid in one of our own power units, and we're going to test it here in a moment. I've got the sample ready, and it was looking pretty clean, and I thought, oh, this will be fantastic, and ran it through the particle analyzer, and the number that it came out with was 2018-14, and we'll analyze these numbers a little bit more in a moment. And I thought, I wonder if that's already borderline. We've got a Rexroth A10 VO pump running, and we were a little concerned thinking maybe we're on the edge, but I looked in the Rexroth A10 VO pump specifications, and it requires you to stay at or better 2018-15. So we were just on the edge for 2 readings and just a little bit better on 1. But yeah, I think that gets us pretty close to answering the pop quiz question, that what you see may not be an indication of the complete truth. We'll have a look at that one in a little more detail here in a moment. So what do some of these numbers mean? Well, let's switch over to a lesson in lunchbox sessions and just think about microns and particles, and Mark will chime in, I'm sure, as needed here. Some of the common ones we bump into, you've already seen them in our slides: metals, elastomers, rust, silica, fibers. These are very common things for us to find in hydraulic fluids that have been in use, and a few other contaminant types along the way as well. Some of these images here will maybe remind you of where contaminants come from. Oh my goodness, look at that. There's a valve plate that was badly cavitated, and you can imagine where all that bronze material went as it was imploded away from that valve plate in a piston pump. And some of those images there made it into our lesson. You saw those earlier in our slides of shame, I guess we could call them. And yeah, a basic breather, I think we mentioned, very coarse. A basic tank top filler cap with a breather typically doesn't have much more than a 40 micron mesh in it. So that's not great for, overall system cleanliness. We've got others here, like this desiccant breather, and the desiccant, of course, changes color as it absorbs moisture, so that's good for helping control with water. But also inside this desiccant breather is a 2 micron basic dust filter, and that's a pretty high performer compared to the basic garden variety 40 micron mesh breather cap. Quite a bit of a difference there. Let's just move along. Fibers we talked about. Okay, so we need to get down to a discussion of what is a micron. Comes from the metric system. If you know what a yardstick is, and a meter stick is only a tiny bit longer, and if you take that meter stick and you divide it into 1 million little increments, you now have what a micron is. And maybe to help give you a little bit more reference, I've got a couple of rulers here. This is a 6-inch ruler from a little sliding T-square, and then let me compare that to a 150 millimeter ruler, 15 centimeters or 150 millimeters. So that's about the length of a 6-inch ruler. And then the top scale of this 150 millimeter ruler is actually broken down into 0.5 millimeter increments. So every single little increment on the top edge of this ruler is 0.5 of a millimeter, but that's 500 microns, 500 microns. Okay, we talked about a human hair being 70 microns in diameter. We talked about servo valves perhaps only having 1 or 2 microns clearance internally. We talked about regular spool valves perhaps only having as much as 4 or 5 microns clearance internally at the most. And so that gives us some reference. Mark, tell us about that 0.00. That's a lot of an inch there. What do we have there? You worked with a machine shop.
Yeah, when we talk about microns, when I originally started in the business, we only had, I was in the US and we had the imperial system. So that's 39 millionths of an inch, which is a pretty small piece of material.
It is indeed. That's a very small increment. I have a hard time remembering what that increment is. So with your machining background, I can always count on you to help remind me of what fraction of an inch that is, and it sure is small. And that's the typical reference measurement we're using for sizing particles, right? Many hydraulic components just have clearances of less than 10 microns. And so there's lots to be concerned about there. Things that are invisible to the naked eye can be boulders inside that system. And how do they get in? Well, there can be some contaminants already present in new fluid. And of course, as soon as you open a container of new fluid, depending on how you handle it, you may be adding to the problem very soon after. And some of these issues here you'll recognize maybe as maintenance issues for systems you work with as well. Quick couplers on mobile equipment, right? Does everyone clean them up and keep them as clean as possible before the coupling? What about a deep scratch in the chrome of a cylinder rod? Can that bring contaminants into the system? Surely it can. So we end up at that ISO standard, ISO 4406, 1999 was a very solid reference. There's a newer version in 2017, very much the same. And there's a code involved with this standard. And so here's one representative number here, 18/16/13. What does it mean, right? Does it mean there's 18 particles of a certain size in there? No, it does not. It means that there is a category of 18 and a category of 16 and a category of 13. Well, these three numbers in the ISO 4406 relate to the number of particles that are 4 microns and larger. The middle number, particles that are 6 microns and larger. Last number, 13 microns and larger. And so now you have to go and find a scaling reference chart to find out what they really mean. So if we take that 18 onto this chart and we look for the scale number 18, we find out that there's anywhere between 1,300 and 2,500 particles that are, let's go back up here, 4 microns and larger. Okay, and that's on a per milliliter basis, on a per milliliter of fluid. All right, now you might say, how much is a milliliter of fluid? Well, let's jump down here. If we look at a soda pop can, some of you will know that as a 12-ounce soda pop can. Some of you will know it as a 350 or a 355 milliliter. Oh, there you go. There's your answer. 355 milliliters fit in a can of soda pop. And we're talking about analyzing the number of particles on a per milliliter basis. You see that graduated cylinder there in the image with 5 milliliters. I've got one here in the lab that's a 25 milliliter graduated cylinder. So that gives you a little bit of a reference to what the milliliter is all about. So let's just go back up there, 18, 16, 13 in that particular case. Hey, you know what? I took one of the jars of the Caterpillar 308 excavator and I got it warmed up. Maybe it's been cooling off a little bit now. And I've got it here in the bottle sampler. Let's just run another count here on the laser particle counter and see what happens and see if it's the same as it was about an hour ago. My sample probably cooled down a little bit, which will throw, but we'll get a little bit of a relative idea in any case. I'll hit the start button here and we'll see what comes out on this next one. The first test I ran a little while ago was 2117.9. And I think it's just about done. And we'll see some paper pop out of the printer there. We'll see what we've got. I'll shut off the bottle sampler, which provides a little bit of push pressure. Oh yes, it looks like we've got a 2017.9, exactly the same as it was about an hour ago when we last tested it, even though the fluid cooled off a little bit. And so if we take that 20 and we look at it on our reference chart here, 20 being our first number, so we would now know that there's between 5 and 10,000 particles per milliliter that are 4 microns and larger. Our second number was 17, so we'd go up here and we'd see on the 17 scale that particles 6 microns and larger, there's between 640 and 1,300 of those. And then our last number was 9. So our last number, drop over into the left column on our chart and find scale number 9. And we'll find out that there's only 2.5 to 5 particles per milliliter that are 14 microns and larger. So the boulders are actually fairly well under control. So if you're looking at this sample and you say, oh, it's dark color, maybe it's really contaminated. Well, when we hold it up to the light, we see it's actually quite clear. Not that that is a good indicator. We just know it's not heavily silted. And what we found out in this sampling is that that oil, from a particle count point of view, might be actually in quite good a shape for the machine that it has to operate in. So that's giving us a little bit of an idea of the particle count there. Mark, do you have any thoughts on that one?
Well, this was probably the biggest step for me in getting knowledgeable in this area, was to realize these scales are necessary to understand. The numbers are just a reference to the scale. You have to get your head wrapped around how big a micron is, because everything starts to affect the performance of your system. And if we're working with particles that are 4, 6, and 14 micron, and the smallest particle you can probably see with your naked eye is around 40, we are always talking about things that are less than we can see with our naked eye. And that's been a big deal over my career.
So true, so true. And maybe we'll just switch over to some questions from our viewers here this morning. This is probably a good time, because Richard Smith is asking a question: can we identify water particles? Well, that is not something that we can do on the microscope, and certainly good quality laboratory equipment do that. Well, this particular laser particle also does a pretty good job of having a look at the humidity issues, the water issues. And so if we have a look at the sample I just took here, it says the relative humidity of the sample was 34%. The other sample said 36%. What does that mean? I think I've got another sample here. Yes, from the loader at the construction machinery down the street, a John Deere 310. This particular sample shows that the relative humidity reading is 76%. Right? And brand new hydraulic oil won't be anywhere near those numbers. It'll be much, much lower. And over time, due to condensation in the hydraulic tank and other issues, the water level may come up. Well, with this John Deere 310, and the laser particle counter was able to look at the water content, the number 76% lets us know that this particular sample is actually getting pretty watery. Can you see the 76% there? And so that lets us know that we're getting close to the edge. By the time we're at 85 or 90%, we may see a milky emulsion. And certainly at 100%, that is the level at which water and hydraulic fluid separate. And most certainly, you will see that it's gone milky, it's become an emulsion. There may even be a clear section of water at the bottom of the hydraulic tank. So yeah, it's definitely a good thing for us to keep track of.
That's a serious number to keep track of here in Canada in the fall. As we start to get on to winter, that amount of moisture level in a machine going into sub-zero weather will start to ice up and cause you more problems too. So it's a good practice to check your relative humidity readings sometime in the fall, so that you can do your planning and get your service done.
Very good point. And Mark, do you want to take that second question that's there from John? John Evan was asking a question. I think this. Do you see it on your side there?
What is the micron rating of a suction strainer we recommend? Well,
let's talk about suction side.
Your terminology always has to be clarified when I'm talking with people about that. There's a difference between a suction strainer and a suction filter. And predominantly, to keep it simple, suction strainers are generally a wire mesh reading. And when you have a 100 or 200 wire mesh, we're talking about the number of openings in a square inch. Whereas a micron reading, then you have to get very critical when you're dealing with filters that are micron rated for suction side, because they'll starve your pump. So you have to be very careful that you know how to read the data sheets, know what kind of viscosity of oil you're playing with. So, There's a lot of talk going on right now about whether you should even have a suction strainer in a unit anymore. And that's an ongoing debate.
Maybe I'll get our camera to come around to the side of one of our power units here, and we'll look at a filter we've got between the tank and the inlet side of the pump. And if we're looking at that, I'll just turn the unit a little bit here so we can have a better look. Here we are leaving the tank and headed to the inlet of our pump, and along the way we've got external inlet line filtration. And yeah, Mark and I had to make very certain that the filter, given the pore size we chose, the opening size we chose, 10 microns, we had to make sure that it was large enough that for the rate of fluid flowing through it, that the pressure drop would not be excessive, causing our pump to cavitate. And just so that we could measure it as carefully as we want to with the differential pressure gauge, we put a test port on both sides of that filter, inlet and outlet, so we'll be able to check up on it. But at least it's mounted externally where it's fairly easy for us to service, as opposed to an inlet, opposed to a suction strainer, which is often mounted in such a way that nobody really wants to ever do the service on it. Wouldn't you say, Mark?
Yeah, absolutely.
Yeah. Okay. Alex is asking a question. Hey, we know Alex. He's saying, does the first number, that's good. That's a good point to bring up. That first number in the ISO rating includes all of the particles that are present also for the other two size categories, because that first number that we're looking at here, I'm just going to scroll back up on screen here on Lunchbox Sessions. So if 18, 16, and 13 is our rating, then that 18, which was the equivalent of, let me find it on the scale again, yes, between 1,300 and 2,500 particles per milliliter, also includes the particles that are larger in the other two categories. So it always stands to reason that as you read your ISO code, that the number will drop down as you read from left to right. Good question indeed. Let's
Last
see.
question there, Carl, I see.
Yeah, do you know how to take that one?
Yeah, sure. Can you briefly tell the difference between a subplate and a manifold block, plus how to make a custom hydraulic manifold block? Well, again, terminology is probably one of the hardest things to really clarify when you're talking with people, and whether it's in the field or whether it's an engineer. There are many things that have different names that may not be familiar with you.
Yeah.
As I interpret that question, a subplate.
I don't think that one really applies to our. Does that apply to our filtration topic today? I'm trying to understand if that plays into filtration to some degree or not. But
yeah, I can't see how it does in terms of contamination, other than we did show the picture of a manifold block.
Perhaps, right.
Perhaps that's where it came from.
Well, maybe we'll ask that gentleman if he wants to send us that question at info@lunchboxsessions.com. I think we would need some more information to know how to answer that one. I'm not sure how we would give that the right context in the time we've got today and the topic that we're on, but we'll be happy to converse with you further. Yeah. And welcome also to new folks who've joined us along the way during the presentation from New Zealand, from the UAE, including Dubai. We've got people tuning in from Minnesota. And great to have you with us from Egypt, from Tunisia. Thanks for joining us here today. All right, so we did a test on the laser particle counter to see that the excavator hydraulic oil is probably in pretty good shape. Yes, we wanted to give you a little bit of a look at what we do with our microscope as well. These types of microscope kits for viewing contaminants can sometimes be bought by the companies who produce high-end filtration. They'll set you up with a lab kit, perhaps even the microscope or some type of viewing device, and to allow you to do what we're doing here. And this is actually ISO 4407. There's a long document with procedures if you want to really do it in a controlled fashion. But Mark and I like to do it because it gives us a relative reference to be able to identify the nature of the materials that are inside the system. And sometimes that seeing is believing. It really helps you understand what it is that's actually in there, so you don't have to just trust the data being sent out by an automated machine. And that's a good process. So on that fritted glass base that's stoppered into the flask here with that membrane filter with 1.2 micron pores. We prepare a sample. Mine's cooling off a little bit. We usually get it good and warm, above 30, 35 degrees C, a 25 milliliter sample. And we add to that another 25 milliliters of mineral spirits to thin it down, because we've got to get through some pretty small pores in that membrane filter that we've installed between the funnel and the flask. And we shake that up to make sure that we get as many of the solid particles that are in there into suspension as we can. We have to have our funnel glassware above here nicely cleaned in advance. And that's done by flushing with mineral spirits that are filtered through a 1.2 micron filter on the end of the hose. And once that's all set up and ready, I put that into the funnel. We run a vacuum pump to create a vacuum value below in the flask. And that is drawing, using vacuum, that is drawing the sample fluid above through that tiny 1.2 micron pore membrane filter that's been mounted, it's been clamped in place between the funnel and the flask on that glass, on that fritted glass base. And so it just takes a moment to draw it through. And then when we're done that, we get a Petri dish ready. The Petri dish is shipped brand new from a lab supplier, and it's left in a little plastic bag for cleanliness. I pried the lid off so that it's ready to go just for the purposes that we have here today. I've got to find my forceps. You'd call them tweezers any other day of the week. And then we take that sample. It should be enough vacuum to draw the rest of the fluid through. We're just emptying out there.
I think too, Carl, where this exercise, while we're waiting for that, is really good. When I'm teaching this in a class, I always ask guys, once they get it focused on the microscope, before they use the software to measure it, make an approximation of how big you think the particle you're looking at is. And they're often very shocked. Somebody will say, well, that's a 4 or an 8 micron, and they find out that's a 200 micron particle. And it's a real eye-opener to see this contamination on this scale.
Good point. Absolutely. Good point. Okay, so I'll lift that membrane filter off of there. I don't know if the camera wants to come in close and have a look, but you'll be able to see where we captured contaminants on that fritted base. There's, it doesn't look like there's a lot there. There's no big dark stain like on the example from the loader the other day. And then we transfer it into the Petri dish. We lay it down in there, get the lid on there soon after, and then we transfer it over to the microscope. And I've got one ready from that exact same sample already underneath the microscope here. So I'm just going to change over to view from my microscope. There we go. I think we should be live now. I'm just going to check my scaling. So you should be seeing particles on screen now from that same sample of oil from a slide I prepped just a little earlier. And as I move around on the screen here with the cross-slide table, you'll see the stars in the night sky. And all of those shining objects are solid particle contaminants sitting on that filter membrane. And I can try to pull a focus on some of them. And I get a little bit more concerned, as I did this morning, to see those yellow or bronze colored ones, because we know they came out of a unit with a piston pump, and wanting to make sure that we understand what level of contamination we've got and whether there might be some concerns. So I'm just going to grab a measurement tool here. I'm going to grab the measurement tool for a circle using the center and the radius. This is software that typically comes with a digital microscope. And the digital microscope we've got here is set up right now to give 100 times magnification if I look in through the stereoscopic eyepieces. And then we've also got on ours, we've got a 10 megapixel camera looking down from on top, and that's giving us a lot of additional magnification capabilities if we want it. So I'm just going to hover over this bronzish, yellowish colored object and click once and pull a circle shape out to what I think is approximately the outer edge and click off to find out that that very large, I don't know if you could see that where you are at home on your screen, but that's a 53 micron measurement. So that's a very large piece. Mark, what's the smallest that you could see with the naked eye typically? What have we typically found?
Typically, it's 40 micron, which is really small.
I'm not sure at my age if I could see 40 microns or not, but
yeah, I think mine's up to about 70 now.
Could be, right? Yeah. Let's go over to the left side of the screen a little bit more. And again, I'll click in what I believe to be the middle of that particle. And I'll pull a circle to what I believe is the outer boundary to find out that that's a 11.45. It's a 12 micron particle. So if you're looking around the screen, you'll see there's a fair number of particles in that size category. You know, that same size happens again in a good number of places. And most of these bright and shiny ones will be metallic pieces, and you might be kind of alarmed. But we've got the ISO code that we took here this morning to let us know that we're 20, 18, and 14, and we are compliant with what, we're right on the edge for two of those numbers, the smallest and the medium size, but we're compliant with what's required by the manufacturer of the pump, if that's the most sensitive thing, right? We'd pick even a tighter number, right, Mark, if we had a proportional valve or a servo valve in there?
Yeah, you usually pick your number, your target number you pick according to what's the most sensitive component in the system, because that's the one you want to protect the most.
Yeah. Let's see here. What else should we? We'll look around for just a little bit more here on the screen and see if there's anything else that we should have a look at or measure. Maybe I'll just do an edit, select all, and I'll get my handy assistant here to. Oh, I didn't do that right. Edit, select all, and I'll just get you to hit the delete key and wipe out those measurements. Thank you. And we'll go hunting with the cross slide table and see if there's anything else interesting. I saw some bright blue pieces this morning. They're very clearly a blue color, and I hadn't seen that before. I always wonder when I see colors what they might be. So yeah, sometimes you recognize the color of the sealant fluids that you're using for sealing threads, and you realize, yeah, stuff is getting inside the system, and so seeing can help you understand the nature. You know, there's something in here that I see that's red colored, but it's only like a red outline. It's almost like a thread of something that's red. I'll just zoom in a bit on that and see if you know, I don't know if you can see a red circle there, and it seems to be dark in the middle, so I'm not sure what exactly that would be. So sometimes this microscopic work starts to get you thinking about materials that are being used in your mechanical work with maintenance. I can't find any of those blue particles that I saw earlier now, but I know they're somewhere on this slide. But yeah, even if we stop here and look at this image, I'll just try to pull a reasonably good focus. There's a pretty good assortment of particles there that are about 2 microns in diameter for the smallest ones that are just shining into your eye to, you know, around the 10 and 15 micron diameter. So it gives you a bit of an idea as to what those particles look like. Perhaps this is a good time to move over to thinking about those devices that help us keep contaminants out of the system. Should we talk a little bit about filters, Mark?
Sure. You want to maybe check a couple questions first? Or?
Let's see. Are there some more questions you want to answer there, Mark? Which ones were catching your eye?
There.
Okay, go for it. Which one caught your eye there?
Well, the comment about are there any other fluids used in construction machinery like or how about other fluids used in construction machinery like final dry?
Okay, so like a gear lube. You must be talking about a gear lube now.
The techniques that we're talking about today, all the data is transferable for virtually any kind of fluid.
Industrial
I've not
lubricants.
had a lot of personal experience with drives, but I know the people that I work with that's their specialty. But the commonality is the terminology, the talk about micron sizes, target levels, what are you looking for? So that is pretty common.
It is indeed. Yep.
The next one there I see, is there any simple way we can use in the field to give us an indication about the fluid situation? That one always makes me laugh because if we're talking about things we can't see, then it becomes a little trickier. One of the more common things that I know in the oil patch when we used to be concerned about water in the system is you would just pour a little bit of oil on a piece of metal, take a torch underneath it, and if you've got high water content, you'll start to get spackling going on with the water jumping under the heat. That was a quick field fix.
Are you talking about that scenario where you basically spatter a bit of
Yeah, yeah.
fluid against a
Just like
fry
a
pan
frying
surface?
pan.
Right.
Yeah.
Yeah. Lets you know if there's some
Put water in
water.
a frying pan and oil,
Right.
you're going to see a reaction. It'll tell you whether you got some water in.
That's a good point. And one of the really key things for working in the field is to work with the team that does some filling. If they're going to fill your tank in the field, the old dirty pail and funnel trick and wiping it out with your shop rag and put it in the filler port in the top and just pour from any old pail or jug. Those are the practices that need to end if you're going to have any hope at keeping particle contamination under any kind of control. And so for many a modern hydraulic system now, there's often a coupling that is provided, and you couple to the side of the tank, and then you pump new fluid in, and usually you pump that new fluid in through a filter cart or some type of filtering device, so that you're introducing oil that's had one round of filtering even on its way into the reservoir. Yeah, okay, there's a question in there from Anmol, how to identify types of particles or metals. Well, one of the best way to identify and be sure is to send your sample out to a laboratory. Obviously, the type of equipment we've got here is limited in its capabilities. There's a limited investment here on top of this table, and allows us to do some field analysis, but ultimately to find out a lot more about the metallurgy and the nature of particles that are in there is to send your sample into a lab and have them do a full analysis on it. And it's really quite amazing now how much data can come back. They're using equipment that is many multiples times more expensive than what's on the table here. And that doesn't even cost as much in the modern competitive age that we've got for fluid sampling. Mark, you probably have some thoughts about sending out samples.
Yeah, well, we would send out samples, especially if we had decent hydraulic particle levels. We would send out annually to get a chemical analysis done on what's in the oil, just to know what your additives may be doing, or if people are dumping anything in the system, what is it? It is fairly inexpensive to do as a test. Usually in Canada here, it run you about $30 to get a test done. It's just a time delay that often will happen, where if we're on top of things right off the bat, it's a really good practice to just do annually. It's not breaking down like an automobile oil would break down. So that there's a big difference there. You can get into more detail at some other time.
True enough. And while we don't have time to go through a full seminar on filters, because that in itself is quite a topic, you know, it is useful perhaps for some beginners in hydraulics who are charged with maintaining hydraulic system to know that a filter is not a filter. They come in a wide variety. A spin-on filter like this might be somewhere between $10 and $20, and this one says it's only going to filter out 10 micron particles nominal. Nominal in this case, it's telling us that the beta ratio is only somewhere around 2. So the beta ratio of 2 lets us know that it's only going to strip 10 micron particles at a ratio of 2 to 1, meaning that this net lets a fair amount of fish go. 2 fish enter the net and 1 gets away, that beta rating of 2, and that's a rating for 10 micron size particles. This one here, this filter element, I took it out of a full pressure filtration vessel. These types of steel canisters are commonly in use when you have to filter oil under pressure on its way, let's say, to a servo cylinder system, making sure that oil is clean before it gets into the valve, which is very sensitive. And this particular filter element lets us know that it's capable of stripping out 3 micron particles, and the beta rating is 200, meaning that it strips out that size of particle at a ratio of 200 to 1. 200 fish enter the net, and only 1 gets away for every pass through that type of filter. And now you're into a filter element that may be several $100s. So, you know, you have to get to know the technology that's out there and what it is that you need, what's appropriate. And Mark, what are your thoughts about switching to higher efficiency filters when you've had a bad run of particle contamination? It's a little tricky to do, isn't it?
Yeah, well, I've had a lot of people thinking that if they had a pump fail, major contamination, the best thing to do then is to get a high beta ratio system or a element. And what that does, though, is it will definitely plug up way faster if the system is contaminated. So I've seen people plug a $300-400 filter element in about an hour and a half of running. So what happens when a system gets contaminated is you have to then progressively start to get that contaminant out of your system. So you start out with a lower rating, you keep working your way up, you keep measuring your oil, you check it against what you're trying to get to, the target.
That's right.
Otherwise, you're just going to throw good money after bad.
True enough.
Because once a filter, especially a return line filters that have, or any filter that has an internal check valve, it's a differential check valve that's trying to say, if that filter gets too plugged, I will bypass the element and then go through the check valve. Well, at that point, you're not filtering anything. So you're kidding yourself if you think they're going to last a long time.
Mm-hmm.
You have to monitor differential pressures one way or another, and there are multiple ways to do that.
You bet. Fabio is asking, can I make measurements of water contamination with the laser? Yes, most good laser particle counters will measure the water content. Sometimes that's an option for a laser particle counter mechanism. Ours certainly has that option. And if you caught it earlier or missed it earlier, we were certainly measuring water content. We had one sample that was up to 76% of the amount of water a hydraulic fluid could hold before it would start to visibly separate. So yes, good question, Fabio. You can usually get a laser particle counter that will measure the water level of contamination, and that's very important. Our good friend Ian is asking a question that, Mark, you might chime in on that one. Is there any merit in monitoring the temperature of oil? You bet. So that if the system operates at a higher than normal, it could indicate some contamination or degradation. What are your thoughts on that one, Mark?
Well, my thoughts on that right off the bat, I'm not a big fan of subjective terms like normal. I always ask people, in order to establish if it's running hotter than normal or lower than normal, you have to tell me what normal is objectively. When I first went down south and I was asked the question, well, what temperature do you like the system to run? I always say like 120 is my goal. It isn't necessarily where I get them, but it's my goal. And they all laughed at me because I'm from Canada and I was down in an area where the temperature of that day was 118 ambient temperature. So yes, you do have to kind of keep an eye on that. It's very important because your seals will start to deteriorate, which then again, as we said earlier, will add to your contamination.
And on all these samples, as dark as they were, one of the first things I wanted to do, since it seemed like they've been neglected for so long, was I gave them that all scientific sniff test to find out if there was a really bad burnt smell, which would have then indicated that the oil is in truly terrible shape. It would be good to send this one to a lab that came out of the loader and find out just what's left of it. But yeah, I think one of the consistent maintenance checks anyone should do with the operation of a hydraulic system is keep an eye on that temperature, know what your normal maximum should be, and stay under it, because the viscosity of oil that will have been chosen for your system as the normal oil will need to be kept at a maximum. Anything higher is going to damage the additive package in that oil and damage its ability to protect metal surfaces. Great question. Andrew, I'm not sure. I don't have an awful lot of experience with the non-flammable fluids. We have a few clients who run it in a metal smelter environment. I know that they're made up of a number of different types of compositions. I don't have any direct experience with the vegetable sourced oils myself. Mark, anything that you have?
Yeah, I've had very little. Maybe in the East we had some glycol systems, but I wasn't too much into contamination at that time. But I'm quite certain, Carl, if someone was to get into the ISO code system, their procedures are very very clear as to the things that have to happen under those conditions. So I would recommend you check an ISO.
Yeah. And Andrew, if you've got some more specific questions about biodegradable, I do have a contact I can't think of his name at this exact moment, but if you email me, info@lunchboxsessions.com, I will refer you to him. He is a vendor of the vegetable-based and other biodegradable hydraulic fluids. He's got a lot of experience with it. So if you have specific questions for him, I'll be glad to connect you with them. And I think that kind of brings us towards the close of our time today. Thanks everyone for joining us. We had some others join us along the way from Colombia, and some latecomers came in from Mexico and Italy, and welcome someone from Sweden who let us know that he's kind of a beginner in hydraulics. So I hope some of these topics we were discussing were useful for you as well. So that's kind of our hour together. CD Industrial Group and lunchboxsessions.com is myself and Owen and Mark you've met today, Nathan, Crystal, Robin, Chris, Ivan, Alex, and Lenore, who all work so hard on our services and products. And special mention also to Ted, Keelan, Emily, and Grant for their contributions throughout this past year. Thank you to Fluid Power World. Our sponsor today was SMC. Thank you. And our next live broadcast will be June 23, when we'll be covering the fabulous topic of servo valves, those valves that have some pretty fine little jewelry, Swiss watch-like mechanisms involved in some of them. You hear about valves with a voice coil and very sensitive, so it's a good thing we started talking about keeping fluid clean first. And we'll see you then on June 23rd. Thanks, Mark, for joining us today in the discussion. Appreciate having you there.
It's nice to be connected again during this period of being away from everything for a while, although I am quite enjoying having some time off.
There you go. Thanks to you, our participants, and we'll see you again soon. This is Carl from lunchboxsessions.com. See you.
All right. Take care, everybody.
Bye-bye.